So, good evening, students. So, after we learned about the basics of electronics and communication engineering in the previous video, today I will be starting with the first topic, power supplies of the course basic introduction to electronics and communication engineering according to the syllabus of VTU. So, the first module, it deals with power supplies and amplifier circuits. So coming to power supplies, we know that most of the electronic circuits need a regulated DC supply between 5 volts to 30 volts. So in some cases it can be derived directly from batteries such as a 9 volt battery or a 12 volt battery, but in most of the cases the DC, it comes from a standard AC mains supply. So this chapter, it deals with how some circuits called rectifiers give the proper DC signals. Okay. So first let us have a look at the block diagram of a simple power supply circuit. Block diagram of a power supply. Okay. So first we have a step down transformer, and then a rectifier, and then a reservoir or smoothing filter. Okay, and then lastly, in the last we have a regulator. Okay, so our main AC mains, it is fed to a step down transformer which converts the main AC into main AC supply mains of somewhere around 220 to 240 volts. Okay, so this converts it into either 12 volts or 9 volts or either 5 volts. Okay, the output of the step down transformer. So this depends on the turns ratio. It depends on turns ratio of the transformer. Okay, so after this we have a circuit called rectifier. Okay, so this one, it helps in getting an unsmoothed DC signal. Okay, so this unsmooth DC signal is then given to a reservoir or a filter circuit which smooths the signal. Okay, so smooth DC. And then the last one, the regulator, helps in getting a regulated or a continuous output. Okay, so this is our final output of the power supply, final output of power supply. So in case you can consider a mobile charger as an example for a power supply circuit, which gives a 5 volt DC signal as its output. Okay, so that gives a step this one. So some of the main components for these are obvious. This has a transformer, okay, and then here nominally for a rectifier circuit we have some different rectifier circuits. Okay, so here this is called bridge rectifier, okay, which we will be studying in detail in the subsequent videos. And then here we have a capacitor which acts as the filter. Okay, and then we have the regulator which has a BJT. Okay, BJT and a diode. So in this case it's a Zener diode. A BJT followed by a Zener diode, you get a regulator circuit. Okay, so these are some different components used for these different blocks. Okay, so next we will be looking into one of the most simplest rectifier circuit. So now we shall start with rectifier circuits. Okay, so on the board now I have a half wave rectifier circuit. This is often referred to as half wave rectifier. Okay, so this rectifier circuit, it comprises of a step down transformer T1, okay, which is connected to a diode D1 and then a load resistor R. Okay, so here the input for the step down transformer is our AC supply of 240 volts, okay, which steps down this voltage to 12 volts AC. Okay, so here both these signals are AC signals from 240 volts. Okay, at the step down, at the secondary terminal of the transformer we have 12 volts. So this 240 volts by 12 volts, it gives us a turns ratio of 20:1. Okay, so now if we so this relation, it can be given as V1 by V2, okay, which is equal to N1 by N2. Okay, 20 turns. Okay, so and then further the diode, we have a diode a silicon diode D1 and a simple resistor RL. Okay, now coming to the operation of this rectifier circuit, let us consider a sinusoidal signal. Okay, so this signal, it comprises of both a positive half cycle and a negative half cycle. Okay, so this figure, the second figure, figure 2. Okay, here we have a positive half cycle coming at the primary terminal of the transformer and then giving us another, the positive half cycle at the secondary terminal of the transformer. Okay, wherein the diode conducts. Okay, as we know, silicon diode, it conducts in the forward bias. Okay, so this diode, it conducts and hence a current flows from positive terminal to the negative terminal of the circuit. And then when a negative half cycle approaches when we have a negative half cycle at the transformer, we have the diode is not conducting in this one, hence because here the diode, it is reverse biased. Diode is reverse biased. Why? Because we have higher negative potential instead of the positive potential. Okay, and hence the circuit is open and we do not have any output at this circuit. Okay. So now coming back to the first circuit of the half wave rectifier, here let us assume that the output of the transformer is 12 volts. Okay, so this 12 volts is considered as VRMS. As we know, it is the VRMS voltage. Okay, so in order to get the peak voltage, so we multiply this RMS voltage with a factor of 1.414. Okay, and hence we get the value as somewhere around 16.989, which is considered to be approximately 17 volts. Okay, so here the threshold voltage for the diode is considered to be 17 volts. Okay, instead of the 12 volts RMS voltage. Hence, when the diode is conducting, the potential here drops by a factor of either 0.3 or 0.7 volts based on the diode being used. Okay, 0.3 it's for germanium, and 0.7 it is for silicon. Okay, so this one I just need to convey you guys. Next, in figure 3, you can notice that we have an additional capacitor called C1 before the load resistor R. Okay, so this capacitor, it is the part of our smoothing operation. Smoothing. Okay. So this is often referred to called as smoothing capacitor. Smoothing capacitor. Okay. And the function of this capacitor is to maintain peak voltage. Okay. To maintain peak voltage when D1 is not conducting. Okay, that is when D1 is reverse biased. In order to maintain the peak voltage at 17 volts, we need a smoothing capacitor called C1. Okay, so that when the primary voltage is first applied to the transformer T1, okay, the first positive half cycle output from the secondary will charge C1 to the peak. Okay, so in forward bias, this C1, in forward bias, the capacitor gets charged, okay, to charge to peak value, okay, in forward bias. And in reverse bias, that is when we have a negative potential here, capacitor gets discharged. Okay, the capacitor gets discharged. So now the a question might arise that how much time it would take for charging the capacitor C1 and for discharging capacitor C1. Okay, let's just have a look here. Yeah, so here in forward bias, let's call it as in forward bias, okay, the capacitor C1 charges, okay, to peak value. This would be approximately 17 volts as we calculated before. Okay, assuming assuming the second voltage at the secondary terminal is 12 volts. Okay, so now the time required for charging, time required for charging C1 would be a product of forward bias resistance, okay, and the value of C1. Okay, so this is normally denoted by tau, okay, which is equal to R into C, okay, and this factor is called as time constant. Okay, so here this value, it goes as for C1, okay, and the R, it would be the resistance of secondary winding, okay, of T1 plus D1 resistance offered by D1 Okay, plus there might be some resistance because of the connecting wires. Okay, plus the can call it as negligible resistance. Negligible resistance due to connections. Okay. So normally when we read in the textbook, it comes as simple sentences. In order to simplify it, I have put it in this form. Okay, for is to understand it easily. So this would be the same even for discharging. Now one might get a interesting question of whether the charging time is more or discharge time is more. Okay, so because we have a higher voltage here, okay, because of the higher voltage at the 12 volts at the secondary winding, okay, we have the charging time is less. This charging time is less and the discharge time is more. That is, in order the when you give a supply at the transformer, the capacitor gets it starts charging at the same time, but when you give it in the negative bias, so then the capacitor, it takes some time in order to discharge completely. Okay. So in the negative half cycle, the time constant would be the product of the capacitor C1 and the load resistor R. Okay, so that would be this one. But why the discharge time is more is because of the value of RL, which is normally higher. Okay, so here on the board now I have some plots, okay, for the half-wave rectifier circuits. So the first one, we have the T1 secondary voltage, that is the 12 volts. Okay, okay, the sinusoidal, the signal considered is sinusoidal. Okay, so here we have plus 17, 0 and minus 17, because we are interested in the peak voltage but not the RMS. Okay, so the voltage across RL without C1, we consider it as just the positive half cycle. Okay, a replica of only the positive half cycles from T1, and this negative half cycle completely ripped off. Okay, and this voltage is considered to be 16.3, considering the voltage drop of the diode D1. Okay, and if we consider C1, that is figure 3, then here we have the voltage as shown here. Okay, the just signal is shown in the black ink. Okay, this is for the reference of this. Okay, so here we have just these, and these small peaks are considered as ripples. These small peaks are considered to be ripples, and these ripples are need to be removed. These ripples are needed to be removed. Okay, are needed to be removed for constant DC output. Okay, for a constant DC output, we need these ripples removed from the rectifier circuit. And how do we do that? That you can by introducing two more capacitors, two more devices, R1 and C2. Okay, as shown in figure 4, we have D1, C1, R1, C2, and then the load resistor RL. Okay, so this combination, the combination of R and C, we call it as a RC filter circuit. Okay, a simple RC filter circuit wherein we can remove unwanted AC signals and get a constant DC. Okay, so this would be our practical half-wave rectifier circuit to get a constant output. Okay, so we have seen half-wave rectifier circuits. Okay, so in the next video I will be giving the techniques for avoiding these ripples or removing these ripples from the rectifier circuits. Okay, so kindly do not miss that video. And if here I would like to put a question as well. If anybody can give the expression for how much ripple we reduce. So if anybody can comment down the answer for it, it would be very much, I would be very much happy for your responses. So kindly like my content, share and subscribe among your friends. Thank you. Also, if any doubts from the video or even my previous videos, please comment it in the comment box so that we can clear your doubts. And any other queries as well regarding electronics, I am very much happy to answer for your questions. Thank you.